Hello, everyone. My name is Jawad Yasin. I am from Autonomous Systems Lab, Department of Future Technologies, University of Turku. That's my workstation, and that is just quickly the autonomous car equipped with an event-based camera. Now I'm going to start my presentation with the slides.
The topic of my presentation is night vision obstacle detection and avoidance based on bio-inspired vision sensors. Here you can see my team, Professor Juha, Professor Mehboob, Professor Hannu, Professor Jukka, Dr. Hashem, and my colleague Sherif.
Going through the contents of my presentation quickly, I'm going to explain bio-inspired camera model, noise cancellation, pre-processed algorithms, segmentation, and in the end, AACA. The motivation behind it is, first of all, I'm going to explain what obstacle detection is. It is one of the most important and essential modules for autonomous cars, drones, and vessels. Of course, sensors are utilized and they're required for observing the environment or surroundings. They capture data, and then that captured data is utilized by different algorithms for filtering the raw data and identifying the obstacles or objects in the vicinity. There are many different kinds of sensors that can be used, such as LiDAR, cameras, sonic sensors, radars, and so on. Different sensors got their different limitations. For instance, sonic sensor has distance limitation. It's a very short range sensor, and environmental noise can also add to the data and would in return require another module for filtering out that noise. And similarly, the traditional cameras, they don't work well in low lighting conditions, and they have a low output or frame rate. As I just mentioned, that traditional cameras have issues with night vision. On the other hand, bio-inspired cameras work well as human eyes, and they have double dynamic range, which makes them suitable for night vision applications. They have been used in many industrial applications since 2014 and are gaining attention of the researchers due to their powerful characteristics. Since event cameras or bio-inspired vision sensors have different output as compared to the traditional cameras, that is, they are asynchronous output, therefore they require novel methods to analyze and utilize the acquired data. As you can see in the output of both traditional and event cameras, the mechanism of the event cameras is that they capture only the intensity change. So it eliminates unwanted redundant data, resulting in lesser computation and high output rate. The characteristics are, high output rate up to 10 million events per second, high dynamic range, low power consumption, and they are asynchronous. From the output, as you can see, they are like, red and blue dots here. These are basically the events. If I speak in very simple terms or layman terminologies, red events are events that are generated from incremental intensity change. For instance, if a pixel intensity increases from 100 to 150, it generates a positive or a red dot, as you can see here. And same is the case for blue for decremental intensity change. Moving to our proposed algorithm, from left to right, first, we capture the raw image, raw events, and observe the environment with event camera, DVS. Then we apply noise cancellation. For that, we eliminate the background activity events, which are due to such as hardware limitations, such as thermal noise and current leakage in switches, and which gives us this image. Third phase, after noise removal, we deployed this segmentation algorithm based on Hough transform, LC Harris, and depth estimation. From there, we detected 3 objects that are of interest to us. And in the final phase, using the objects and the depth or distance of the object from the camera to perform runtime asynchronous adaptive collision avoidance algorithm, AACA. Now, here's the scenario. This scene was captured by Davis camera, which can capture grayscale image and events. The camera is fixed and a person is running in front of the camera. As you can see, the events can describe the scene well, and the person moving in front of it is captured without any motion blur. However, as can be seen from the traditional camera video, it's quite difficult to differentiate and detect by the obstacle moving in front of it because it only looks like it's noise. The limitations of traditional cameras in real world include various examples, which include fatal accidents such as Tesla accidents, where the system failed to differentiate between a trailer and sky, or quite a recent one, which was Uber self-driving taxi fatal accidents, where the system failed to detect the person in front of it on zebra crossing. The video can be seen from this link. The source is The Guardian. Now I'm going to jump to our asynchronous adaptive collision avoidance algorithm. In this algorithm, we are considering each object as a rigid body. Therefore, we estimated the relative velocity of the center of mass of each object. For that, we calculated the distance traveled by the vehicle after t seconds and extract the apparent velocity of the object by calculating the point of impact. Mathematical equations are given in the paper, and they can also be derived by using simple maths. This AACA algorithm is built on top of our previously developed collision avoidance algorithm to tackle multi-priority obstacle switching. In this algorithm, we assign priorities of the obstacles based on the calculated POIs. POI is a point of impact. The highest priority is given to the closest POI. POIs are updated at every interval. The reason is that in case a new obstacle is detected or an already detected obstacle, its relative velocity changes in such a way that its POI becomes the lowest. So that is updated accordingly immediately. Furthermore, the AACA algo is also able to tackle with multiple obstacles in parallel and calculates the distance between them and reroutes the vehicle accordingly. For instance, if there are like 2 parallel obstacles with same POIs, the algorithm will calculate the gap between the obstacles. If the gap is more than the defined safe distance, that is calculated based on the dimensions of the vehicle, then if the safe distance is more, then the algorithm will reroute the vehicle to pass through the gap. Otherwise, if the safe distance is less than the defined safe distance, if the gap is less than that, then the algorithm considers those obstacles as a single obstacle to deal with it accordingly. And the results we got are shown here. The first row is for the event camera. Second is the same scene utilizing traditional CMOS camera. Here, the raw events and the raw image is detected. As you can see, there's after filtering it, there's a very distinct person or an object in front of it. Here in the traditional camera, you can hardly notice anything, and it looks like it's only some noise or something which can easily be missed, as you can see over here in the G and H figures, which are mostly like some scattered dots and some lines which hardly make any sense. And that is the reason why some state-of-the-art systems fail to recognize obstacles in front of the camera. However, in our utilizing our approach, we found 3 obstacles, which were, of course, like this is a person. That's one of the foot of a person, which for some reason was a bit different, got diagnosed differently, but it's not of that big of a concern. The reason is the relative movement of this part of the body or this object will be the same as that, and it will be dealt with accordingly when it's updated. Now, if anyone's got any questions or suggestions or constructive points, I'd love to hear, and I'd try my level best to answer. Thank you very much.